Hello everyone, welcome to this session. In this session, we'll provide you a brief introduction to the ARC package. I guess you may ask about what is ARC. So ARC here, ARC stands for Automatic Rate Calculator. It is an open source package that is hosted on the same organization as Reaction Mechanism Generator on the GitHub. And you can find the ARC package under this link. So the ultimate goal for ARC is to achieve end-to-end automatic electronic structure calculations that are relevant for chemical kinetic modeling. So we know the quality of RMG model is heavily depends on the quality of parameters used. And there is no guarantee that we can always find some accurate data from literature or other source that for our sensitive species or reactions. And also by simply using the RMG estimation can cause you or can leave you a high uncertainty for your model prediction. And maybe the only way to kind of make your model better is you have to calculate them by yourself. Um, so So in that case, we know something about the molecules or the reactions we care. I mean, by for example, the representations for this species or the reaction. And what we would really want is their accurate thermodynamics or rates, and probably even better in some useful format like not a polynomial or a Arrhenius formula. However, it is a pretty complex process in reality. So from simple representations like smells and or Inchy or reaction family, we first need to convert informations into 3D and make a kind of a reasonable guess for the structure of the molecule. So there's the conformer package that can do that for us. And later we need to provide the kind of the initial guess for the geometry of the molecules or the transition state to the quantum chemistry package such as Gaussian or Orca to help us optimize the geometry and do the frequency calculation, energy calculation, etc. to get the properties we want. And for transition state, usually generating a reasonable transition state is really difficult. Um, you can do it manually, however, it requires kind of high expertise. There are also some transition state gas generation package can do that for you. However, you have to know how to use them. And once you have done the kind of each step of quantum chemistry uh, calculation, you have to inspect your results. Either visualize the data or check the, say, for example, frequencies, whether it makes sense or not. And all this kind of quantum chemistry calculation is really requires like some advanced computational resources, and you usually have to deal with job management package like Slurm or OGE. Therefore, you also have to know how to submit like this kind of calculation to the cluster. And once the quantum chemistry calculation work is done, you still have to pass them to other package, for STEMAC calculation or transition state rate calculation to get the thing you want. So you can tell this is a pretty complicated process and it involves many steps, many different packages. You need to understand how to use each package, and you need to provide the input file, parse, kind of read the output file, and have to submit the job, upload the files, download the files, etc. If you are a quantum chemist, Uh, you if there's something can do that for you, it will save you a lot of uh, working a lot. If you are not like a expert in the quantum chemistry, and probably if there's some package available for you to do everything, that it can free you from doing or learning all of this thing. So, and actually Arc is designed to kind of do everything for you, so you can like more focus on the modeling job. There are advanced functions in Arc that to achieve that purpose. So Arc has a tailored input-output module and a job management module that can, write the input files or submit scripts according to some template. Arc can submit jobs, monitor jobs, or synchronize files automatically. Even if you don't know how to read the output from, quantum chemistry package like Gaussian, you don't have to worry since Arc know how to analyze the results. It can parse information like geometry, energy, frequency, etc. It, it also knows the error message and figure out what's going wrong. And if there's something wrong, Arc can check it and figure out the the patch for it. So Arc can automatically trying to solve the problem for you. And each individual module work for one of the purpose, and you really have to kind of serialize them together. And Arc has customized workflow to combine everything. So not to mention, Arc can do a workflow for thermodynamic or race calculation. It can also do something like bound dissociation energy calculation, bound additivity calculation, or frequency scaling factor calculation, etc. Here, here I show a workflow for thermal or recalculation we use in the Arc. So starting from the molecule or transition state information like XYZ or SMILES, Arc will call some package and generate the conformer. And once that's generated, it will feed to the quantum chemistry job to do the optimization. It will check whether the optimization is converged or not, and if it is converged, then it will parallelly launch the rotor scan jobs, frequency jobs, single point energy jobs, and beside the check for each individual jobs, Arc also have like a self-correct strategy to see, for example, whether if there is a lower conformer being found, then probably it's better. It is more correct to use the lower energy conformer, and Arc will automatically repeat the process for you. And for example, if the calculated frequency doesn't make sense, and Arc will have some strategies to adjust that, and relaunch the whole workflow for you. So once everything is done, kind of uh, at this point, we are done for the quantum chemistry calculations, and the results of quantum chemistry calculation will be summarized by Arc and fed as a desirable input format for STEMMAC package like Arcane, and Arcane will then calculate the partition functions and even the heat capacity, rates, or other properties you like, and export them in the format of RMG database or chemical models that you can directly use for model generation and further model improvement. Since Arc can achieve this workflow, then the whole iteration process will be really simple. You know something from, for example, sensitivity analysis of what molecules you are sensitive to. You simply fit the information of this molecule to arc. After a while, when arc finish the calculation, it will provide the, for example, thermodynamic or the kinetic library of RMG, and you directly feed the library into RMG, and you can further do the model generation or model improvement based on RMG. And so you can tell ARC really is the whole iteration process, right? So at this point, ARC is still something that just on slides, and probably it's better to show the function or how ARC works, actual work in reality. And then if you are interested in ARC, then probably we can go through some setup and some discussion later, right? So assuming you have ARC installed on the computer, so there will be an ARC folder here, and in ARC folder there will be a IPython. In the IPython, there's a folder called demo. It's already included in the default package. So as long as you download it from our GitHub, you can find this demo package, demo folder, right? And let us open a Jupyter notebook to run everything. So Arc also has its kind of running environment, just like RMG. So it also powered by Conda, so you can do Conda activate Arc environment. And then you do Jupyter notebook to initiate the Jupyter notebook. Then there will be a Jupyter notebook pump up and is already in the demo folder. So let's open the Arc thermal demo. So in this demo folder, it shows that by simply using that short script, Arc can calculate thermal dynamics properties for the molecules you assign it to do. And the first step is, of course, import some important module used for Arc. Oh, it is worth to mention, this is one way to run Arc jobs, or you can run Arc job in Jupyter Notebook to use its API. There's other ways to run it, by input files. We will talk about it in the later part of this session. So Arc support multiple ways to feed, molecule information. For example, you can provide just the smiles of the molecule. You can provide XYZ for the molecule. You can, yeah, this is the same way. And you can also provide the adjacency list of the molecule. So there are multiple ways to do that. And due to the time limitation, let's just consider two molecules. One is the species 2, which is the hydroxyl radical, and species 3 is the methylamine. And now we create a species we want to calculate. In this session, the ESS setting is just I want to use Gaussian that on my RMG server, and I want to do conformer jobs, to generate some conformer and find what's the kind of lowest conformer according to some cheap method. And then I want to do optimization, of course. Due to time limitation, I don't want to do a fine grade, which maybe get more accurate data, but makes the cost a little bit higher. I want to calculate frequency. I want to calculate the single point energy for the conformer. I want to do a rotor scan and get the rotor partition function. This is not a reaction, so I don't have to do IRC calculation for that. So we can name whatever we want. We just name the Arc thermal demo here for the project name. And we have the species we want to calculate. We have the yes setting settled. We have job type settled. For this, you can apply and you don't have to apply it since arc have some default values for the levels to be used. However, for here I just use B3 leap 6-31G DP for the optimization level and M06-2X CCPVTZ for the single point level. And um, due to there is no bond additivity correction for this single point energy stored in RMG or in the arcane, I won't use bond additivity correction for this. So by shift enter, let's just run it. You can tell arc initiate this job at pretty late here. It will go into the Gaussian on RMG. This is the kind of the level of theory we will consider, and we are not using a fine grade for the optimization. So let's see what species we are consider the hydroxyl group and methylamine here. So hydroxyl group, there is no dihedral, right? Dihedral bond, and there's no rotor. However, there is one dihedral, right? Dihedral bond, and there's one rotor in the methylamine. So you find it, and you will like launch the scan job according to this rotor. First, you will try to do some conformer generation, and this is what you find according to force field. This is the geometry of that molecule, and then based on the force field, it will launch the conformer jobs, and I mean this is a slightly higher, usually either quite cheap DFT or cheap semi-empirical method to further improve this force field result, and it will launch to the server. And then while waiting, it will then launch jobs for methylamine. Since it has a rotor, then there will be something related to conformer generation, and ARC has its kind of smart designed conformer generation algorithm, and according to that, it finds there will be just three cluster kind of for three possible cluster for the dihedral angle, and actually you can tell it's a methyl group, so there will be no differences, and ARC also can tell that, so it will figure out there is just one conformer to be used, and this is the force field result from this kind of analysis, and this is the geometry, and then it will launch the optimization according to that. And meantime, the calculation, the DFT I use is pretty cheap, and the molecule is pretty small. It finished pretty soon, and it will just print out the kind of optimized geometry at this level, at the optimization level we want. And since the optimization is finished, then it will launch frequency calculation, single point calculation, and scan calculation. And meantime, OH is also finished, and you can tell there's a line cut most stable conformer that is isomorphic with the 2D graph. So it actually check whether the optimized geometry represents the same molecule as the initial molecule we want to calculate, which is really useful. So it makes sure the calculation makes sense. It won't spend a lot of time calculating something we don't really want, right? So it will then launch the optimization for hydroxyl group, and the job is done pretty quickly. And further, it will launch frequency job and single point job for hydroxyl radical. Okay, then afterwards, all kind of jobs for hydroxy radical is successfully converged, and you can tell the single point for methylamine and the frequency methylamine is also done, then we are waiting for the scan job for methylamine. Usually, it consists of several, you know, it consists of constraint optimization and single constraint optimization for several points. So it will be more costly than single than some other optimization or frequency jobs. Actually, let's talk about kind of uh, the folder structure of it while we are waiting for the last scan jobs. So if you are launching jobs by API, then there's a project folder, and in the project folder we can find the project we just launched, Arc Thermal Demo. So in the Arc Thermal Demo, there's the arc.log, which is the same as what we see here without showing the geometry. And there's a calcs folder which contains all the calculations, you know, the calculation output for the quantum chemistry. Like for example, the conformers, the frequency optimization, single point, etc. If we open that, it consists the output file, the input file, the generated by Arc, the checkpoint file from previous run, and the Smith script. And once everything is done, we can open the output file, output folder, and all the output, including the library result, the kind of the information for each molecule is stored in the output file. And there's a restart YAML, which is used for restart the job. For example, if the network connection is broken at some point of your job running, uh, therefore Arc will be shut down, or your computer is for some reason just running out of battery, then the process is killed, right? Then you can simply go back to this folder, um, launch the restart the YAML file. I will talk about it how to kind of restart in the later section as well. And by doing that, you can restart a job. And it is pretty simple. You won't lose anything since it is already there. It won't relaunch the job as either. Okay, that's great. So the scan job at this moment is also done, you can tell. And the arc will, automatically determine the symmetry of the rotor and, generate a plot of the scan for you. And now all of the jobs are finished, after 8 minutes. And then it will try to calculate the thermodynamics. It will get the enthalpy, entropy, and kind of their dependence at different temperature. It will do the same thing for methylamine, and once everything is finished, it will compare the results to the kind of RMG estimation, I guess. Yeah. It is not. Yeah. There shows so the thermal library and the thermal library used for RMG estimation. So generally the result is not bad since we're just using DFT instead of some pretty accurate data. It is okay, and this is just demo. Afterwards, everything is terminated. We are all set. And at this moment, if we go back to the output file, then there is the thermal parity plot we just saw. There's a thermal info, which include the kind of the information in this thermal parity plot. There's the status. We can find, okay, everything is finished. It passed the isomorphism, or kind of I mentioned, it compared the molecule, and this is the molecule we want to calculate. It makes sure it is that, and this is the results, the path to the results, etc. This is the status file, and in the species, then we have the species we calculated. It has a figure that contains kind of the heat capacity, entropy, etc. What's the fitting, and what's the actual value. And the rotor figures I just made, we just saw, we just saw in the Jupyter notebook, and we have the geometry, the XYZ, the frequency output in this result as in this output as well. We have the output from Arcane, and we have this file, the YAML file, which contains all the information of the calculation. Kind of so not all, but kind of summarized calculation, which can be used for uh, kind of reuse in when you calculate some reactions for this species, or generate the pressure dependent network for the which involves this species. It contains some the representations, some basic like attributes. This is the kind of coordinates. It has the what is this? The mass of each atom, etc. You can find everything here. And in the next session, actually, we will see how you can reuse this YAML information to calculate a reaction. And this is about the species, and there's RMG library. Since we calculate the thermal, we'll generate a thermal library. And it is directly rated into RMG library format. So if you just copy paste that into RMG database, then you can, import or read this thermal library when you doing RMG model generation. And on the server, I can also show you on the server where everything is in the RMG on the RMG server. So let me go to my RMG server. You will find there will be a folder called runs, and let me clean up. And in the runs, there will be a folder called arc project. In the arc projects, we have the arc thermal demo we just shown. So we can also go to arc thermal demo, and let's go to the OH. It's basically the same thing we'll see here. There are multiple ones since I kind of tried the script or the Jupyter notebook before this session many times, so there will be several instances. However, it is the same. So if we go to one of the folder, say 699 maybe, and it's contained the checkpoint file. It contains the standard output and the standard error file from the submission script, and the input file, and the output file of the quantum chemistry package. Okay, so this is the arc thermal demo, and let's look at the arc reaction demo. So arc reaction demo is also in the IPython demo, arc reaction demo using YAML. So let's go back to this and open it here. So here, as I just mentioned, in the kind of the calculation for each species, it will generate YAML, which kind of summarize all the key properties that you can reuse in the future. So in this kind of demo, we won't do any further electronic structure calculation. We just reuse this YAML file and calculate the reactions. Assuming we have the YAML file for ethanol OH, the ethanol radical, water, and the transition state. So it is in this YAML file adjacent to the demo Jupyter notebook. So we have the YAML of each one. Then, since we have everything, it is not important to assign this it won't like since Arc knows these are the YAML file, it will read it, it find I have everything. Even though you assign a kind of the job type here, it won't be like effective, right? So once you supply the species information, the reactions is just mention what are the labels, what is the reaction label, what are the reactant or products on each side, and what's the TS. And then Arc will go through that. Okay, this is a level, but it's not necessary for this case. We have this species, since everything is down, there will be no, quantum jobs. It will just focus on this reaction. It knows kind of the energy for each side, and it can directly compute the rates for that. And this is a kind of a Python uh, um, class that use or Python instance that used in RMG. And this is thermodynamics for each involved species. It will loading RMG database to do some sort of calculations. And after a little bit, it will generate the reaction library for you. So again, you can copy paste the reaction library into RMG database and use that for further model improvement. Okay, now the job is finished. You can see it also summarized the thermal for it. It also uh, kind of get the rates and search for all possible rates in the RMG database for comparison. You know, the rates we just calculated by Arc is looks reasonable, and it is done. And the same thing. So if we want to find the kind of the RMG library generated by this Arc job, we can go back to this is Arc directory. There will be a project file, and we go back to this. Let's check what we call this project as reaction TST. So if we're trying to find reaction TST, then we'll find the output in the RMG libraries. We'll have, yeah, we have both thermal and kinetics since we have, it also calculates thermal since it has enough information. So in the kinetics, it has the species dictionary that automatically generated. It has the reactions that written in a form can be directly read by, by RMG. Right. This is the two demo that I want to show. The logic is Arc is pretty new to everyone, and I guess if I directly show the installation process, it will ask, why should I install this? I don't even know whether it works. So at this point, you see, it works, right? So if you are interested, then please follow me. I will show some of the kind of guidance for the first time setup. So to set up the Arc, um, you need to clone the Arc from its from the GitHub, right? You can, oh sorry, you can copy paste the kind of the path. Uh, let's go to the Arc repository. So this is RMG organization on the GitHub. There will be you can easily find Arc, and by hitting code and copy, then in the terminal, I don't have a terminal here, so let me just release the terminal. This is my terminal. So in the terminal, you can just do git clone and copy paste the thing into the directory you want to install. Then it will download Arc. Since I already have Arc, I won't download it again. So my Arc is in my apps folder here. This is my kind of installation directory for Arc. And afterwards, we need to create an environment for Arc file called environment. So we can do const environment create the thing, right? Directly, you can supply this and environment, but you don't have to since there is just one, since Conda will automatically read it. And let's see. Afterwards, you have to add the arc directory, this directory, or where you installed in your computer, to the slash the home the bash rc or the zshrc file. If you're running Linux, probably you will have .bashrc under the home folder, and if you are using Mac OS, you can find the zshrc under the home directory. So you can directly run this in the command line, or you open the for me zshrc and add extra line like export Python path since mine is apps arc. Then whenever you run your code, the kind of the system will know, okay, this is a Python path, and it will treat arc as a module. Yeah, since I already have it, I just remove it. But for your case, you want to keep it. Okay, so then we highly recommend you to create a .arc folder at home, since kind of when you created a .arc folder, then you can put your customized settings, input file, kind of input templates, submit templates, and without really mess up with the Arc source code. So you can do that by make directory home.arc, and there will be a .arc file. So we can copy the. Let's look at the kind of Arc folder. So this is the Arc folder. There in the Arc, there is settings. So in settings, you have to copy inputs.py, settings.py, and submit.py into the .arc folder at the home. So we copy it, going to yeah, you can now do it in the Finder or the file explorer, since the .arc folder is kind of hidden. So you can run this script or this line to do that. I won't do that, since I already have them already set it. So I will talk about how to modify them later. But before that, I want to go to mention that Arc is a one-to-many kind of client. So, for example, if you install Arc on your personal computer, you can directly use Arc to visit, the servers you running the kind of the quantum jobs, right? And there can be many, since different servers may have different packages that you want to use, and Arc allows you to achieve like connection between different servers. However, to achieve the connection, you need to generate a kind of RSA key so that uh, you know the server and your personal computer that they can communicate without you know input the password, etc. So they will simply communicate by your username and this key file. This is just a very general thing. So maybe you already have them generated. If you don't, you can go to our documentation to know how to use it, or just simply like search Google search for how do I generate the RSA key and how do I copy the public key to the server. Then it will give you back the answer. Okay, so next, of course, we have to set up the settings. Let us um, let me open the setting file and show you what it looks like. So let me just open the settings that within the arc. So let me open so settings.py is in the settings. So we want to open the settings.py, and in settings.py there are two things that you highly possible need to be changed. So one thing is you need to set up the servers, kind of inform Arc what are the host um, you are available for, and what are the cluster software or the more general job management software or the queue software you are that are running on the server. For example, on this server, Pharaoh's OGE is running, on the RMG Slurm is running, etc. What's the address for the host? What's your username for the host? Where is your public key for your like local computer or local cluster? You can set up several different, servers, and you can also set up a local one if you want to also run jobs locally. So this is very important, and for kind of 100% sure, you need to modify it to make it suit for your situation or your information. This one, it is not always necessary. How so? However, I recommend you to like append some information so get Arc understand what are the quantum chemistry package available for you and what are the servers that are running these softwares. These are the default job types. Once you're setting this in the, no matter you are running by API or by input files, you don't really have to uh, provide the job types again if it is the same as here, right? If you remember clearly, then for both demo I showed, I provided job types for that, and currently it supported ESS, several ESS like Gaussian, MoPro, Orca, QCam, TerraCam, 1D main, etc. So I guess this is something you won't want to touch. You can touch this block. It kind of showing some preference for the kind of level theory or the you want to run on some specific quantum chemistry software. However, if you're not familiar with that, you don't really have to change that. This is something you may want to change. So for different queue package, there's different like command to submit the thing. For example, for check status, Slurm use SQ, but for OGE and PBS, it use QStat. So I guess you don't have to the thing usually for this part. I mean the command part you don't have to change. However, the reference may be different from case to case, and you better ask for your if by default if this doesn't work, you probably need to ask your server administrator for help to set up to kind of enter to know what are this kind of binary are located. There are many of them, so better to check each of the one that end with underscore command. This is something you don't really want to, you don't have to touch. You don't have to touch input file name, output file name. You can, but you don't have to. This is default level theory. Here we show some kind of a best practice ones, but you can change them if you like, but you don't have to. This ORCID default option dictionary, you don't have to change them either. And we have some settings about routers and scans. If you don't understand the kind of the concept here, by default this should be run, you know, kind of pretty robustly. And at the end, there's something about default job settings. So if not like provide any job settings, so it will by default use 14 gigabytes memories, 8 cores, and run at most 120 hours, etc. You can set default job settings here, but you can also kind of provide individual information for each cluster. If you don't know any of them, you can ask your kind of server administrator for information about how many cores you are available to use, how many memory, etc. Right? So again, to set up the settings.py, you really need to modify the server's information, and you need to check whether this command works for your case. Usually it works, but in case it won't, right? So this is about settings.py, and if you go to submit.py, this is something for sure you need to change. In this file, I will say in this file, there is a dictionary to store all the submit scripts. So the very top level is the server. So I have these three DDB servers, so I have to have a key for that. And then in the values of that, I kind of listed all of the available, quantum chemistry package as the key and provide the kind of template for the corresponding like package. And I will highlight something you probably need to change for sure. One is this line. This is for partition. So, different cluster have different names of partition. So this is something you really have to change. And different package may have different ways to load modules. So this is something you also want to change. I mean, the way to load modules. Sometimes you need, sometimes you don't. Uh, the third thing you probably want to change is the scratch folder. Different, cluster have slightly different kind of ways to organize the scratch folder. So probably you also need to change that, and probably you also need to change how the for example for this case Gaussian is set up. So in short, I guess you have to rethink about the partition, or you have to enter, you have to know the partition that are available on the cluster. You have to know how the quantum chemistry package are loaded on the cluster and how it is initialized. And third, you also need to know scratch folder for you. However, all of this thing can be, you know, um, can be learned from the server administrator. So I guess you can easily change this. I guess he or she will definitely help you to modify this since it is kind of easy. We have different examples shown here. So we have Slurm, we have this is about OGE, how OGE is written, and at the bottom I guess we also have PBS. So take a look, right? This is for submit. And another thing is inputs. So let's look at the inputs. So inputs contains kind of the template for input, and it is kind of convoluted in the implementation in Arc. So normally you don't have to change that. To summarize the kind of the more complicated setup here, which involving modification on test, you need to go to the settings.py, add your server information, and check if the kind of the command works for you. You also have to go to the submit script, kind of supply the template, or using the template examples we provided to build up templates for your cases, right? And this is about setup. Then in the production run, actually we don't use the API. I mean, you can still use that. It's pretty convenient. However, for most cases, we just simply use input files, and by composing a input file, we can launch Arc and wait, Right. So input file can be relatively simple since we have a lot of default settings in the settings.py. Then if you don't have to change settings, you don't have to apply them as arguments. So the only thing that required is project and the species involved in the project. And however, you can definitely tailor that. You can assign I mean, again, you can assign uh, the software you want to run and where to run them. You can assign the job types to run, kind of the um, configuration for each job, and what's the level of theory you want to run. So we can do a quick example for that actually. Let's go to the Arc folder, maybe in the project where it's projects. So let's do another one, maybe called test. Let's just call it RMG workshop since it is designed for that. So let me do that. So we can simply do project example, right? And maybe instead of running default settings like doing OPTs, etc., we can do, Arc also support composite method. So just type composite method and for example CBSQB3, which is quite commonly used, and provide a species. Let's do a very simple species like nitrogen, maybe. Although you may not actually run it in your actual work, but this is just demo. So nitrogen, and afterwards, what we have to do is let's open a terminal. So this is our terminal, and we first have to go cd this folder. Okay, we are already there, and we have to, of course, activate the Arc environment, and then we need to find where's the Arc main script located. So it is under the path you install Arc. For me, it's under apps Arc, and there is an arc.py file that is the main script for Arc, and then you supply the input file. So before doing that, I will suggest you to modify the thing we just created. So we created a YAML. So actually, all the Arc input file is written in the format of YAML. Maybe you can tell it. And since it is parsed by YAML parser, you have to write it in. Also, you have to write it in YAML. And to make it to make the name make sense, then we better change it to input their YAML, right? And then we can let the Arc main script to run this input file. So it's running. Let's assume something bad or something weird happens. The job is interrupted at some point. Then you can find there is a restart YAML. So the way to restart it is by, instead of supplying input.yaml, we can supply the restart.yaml. So, by restarting it, you will figure out, okay, we have this job being running, and you will check this job. And if it is, during our interruption, it is done, so it can figure out it's done and directly read the output for the job, and then further launch everything, just as nothing happened. It's just go through the same workflow as the thermal demo we just showed, so we won't go further. And this is how we actually use it in the in the production run. Okay, this is kind of all about today's session. We learn what is Arc. Arc try to achieve end-to-end calculation for properties that are relevant to chemical kinetic modeling. So even if you are not an expert in quantum chemistry calculation, you can still use Arc, and Arc can do everything for you. And the current kind of status for Arc is Arc already achieved robust calculation for thermodynamic properties, as you can tell. Doing transition state theory calculation or recalculation is a little bit tricky. We recently added some transition state generation algorithm, and currently Arc support 3 types of Q software and one and 6 type of electron structure calculation tools. If you want to learn more about Arc, please feel free to go to our documentation. There is a really well-written documentation including more details about installation, how to running Arc, provide examples of writing Arc, input files. There are some advanced features I don't really have time to introduce today, and something else. And we also have another video tutorial if you want to learn this kind of advanced feature. It is hosted on YouTube. If you go to this, address, it will show you the ways to do like conformer generation, rotor scan, etc. Thank you, everyone. This is all about Arc introduction. I hope you are interested in Arc, and I hope you have a chance to try Arc and let Arc kind of ease your work. Thank you.